Hello, and welcome to CAS latest SciFinder N webinar. My name is Daryl French. Today, Gary Gustafson, Gianna Frunner, and I will be demonstrating the use of the Retrosynthetic Planner in SciFinder N. In this webinar, you will learn how to explore the alternate steps available for each transformation in a retrosynthesis plan, and select those that create the scheme best fitting your needs. We will use the Plan option functionality to alter scheme features, thereby optimizing the synthetic approach. We'll show how to control the weighting of yield, evidence, and atom efficiency characteristics so that relevant schemes will be created. And finally, we will use the predictive capability to design pathways to unpublished or novel molecules. Now I would like to introduce Gary Gustafson, who will deliver our first example. Thank you.
Thanks, Daryl. Yeah, we have a lot of great capabilities to show you today. So let's get started and go right to the demonstration. For our first example, let's say we're interested in a compound we came across in the literature and we'd like to find out what would be involved in synthesizing the molecule. I will start by searching a substance. I can do that one of three ways. I can type in a name, which is what I'm doing here. Or I could type in the CAS Registry Number, or I could draw the molecule, but I'll search it this way. And here are the results of our search. You can see we get a number of references, reactions, and suppliers associated with the substance search return. Classically, if we were trying to put a retrosynthetic scheme together, we'd have to read a large number of those articles, go to experiments, read a bunch of different experiments, see which one's the best, or maybe kind of cobble a scheme together from several different experiments. Once we figured that out, we would likely have to check on the availability of starting materials. Some materials would likely have to be ordered, so we'd have to look at the suppliers for those materials, compare pricing over a large number of websites. What we hope to present to you today is the retrosynthesis tool can kind of be a one-stop shop for all of that, making the process a little less tedious and much more efficient. So let's look at a retrosynthesis. There are two ways I can get at that. I can click on the structure here. It brings me to this flyout window, and you can see there's a hyperlink here to start a retrosynthesis. I want to show you the second way you can do that. And if I'm in the structure editor of the CS Draw tool, I can upload that to the search bar, change this over here to reactions, and we see we get this button here that allows us to launch a retrosynthesis plan, and that's what I'll do. So what the retrosynthesis tool is now doing is accessing the repository of index transformations we've accumulated over the last 110 years and using its algorithm, finding the best ways to make the molecule. The different options are scored through a process I'll discuss later, and the top scoring scheme is displayed here. Roll it up for you a little bit. So what we have is a four-step synthesis to make our target molecule here. What we do in the retrosynthesis planner is deconstruct it step by step till we get back to commercially available starting materials. We associate all the different experimentals we find for each transformation with the transformation here in the Steps tab, and we cite the highest yielding transformation in this scheme. So we can then associate all these yields to give an estimated yield for the scheme. And for the commercially available starting materials, we can go to our ChemCats database and associate pricing information. And once we couple that with the yields, we can then calculate an overall price to make 100 grams. In this case, it's $351. So, and then I already kind of started to talk about the second tab here. For each step in the transformation, you can see I can highlight them in the scheme by flying over them in the Steps tab. For each one, we provide two pieces of information. First of all, we provide the evidence that we found in our repository about this transformation. In this case, there were 4 different publications that discuss this transformation. I can bring those up. I see the first 3 here. I can bring back the rest by wanting to see all the reaction summaries. So you have that information there. And then the second piece of information we supply for each transformation is other alternative steps we found, other ways we found to make a given molecule. So there were 12 other ways that we found to make compound A, and that can be something you can take into account if you don't like one of these specific steps. As we look at this scheme, it's actually pretty good overall. 3 of the 4 steps are greater than 93% yield. We do have one step that is a 60% yield. So perhaps if we could do better there, that would kind of help the overall scheme. So I can click on the Erlenmeyer, or I could have clicked on this hyperlink over here, and this will bring back the 4 different transformations we found to make this compound B. And the first one's up here. As we look through them, I actually see one down here that is a 92% yield. So that looks promising. So I'd like to maybe consider using that instead of the one I've got. And so all I would need to do then is just click select. It would then substitute in that transformation of the scheme. And since the materials to make that are different, everything upstream of that would change as well. So once we substitute that in, I can go back to my overview tab, and where it was 51% yield and $351, it's now yield's gone up to 79% and the price down to $263. So you may ask yourself, why wasn't this the top rated scheme? The tool's algorithm considers a number of factors when prioritizing schemes, and we will talk about that in a little bit. As it relates to this scheme, a protecting group was used, and none of the atoms from that protecting group get incorporated into the final molecule, so that is viewed as wastage of atoms. Further, this scheme is requiring 5 transformations to make the final product, whereas the one we had previously only had 4. These combine to give the scheme a lower priority.
Hi, Gary. Before you move away from this section, can the default criteria be changed if I'm less concerned with features such as atom usage?
Great question, Daryl. Let's talk about the criteria that go into determining which schemes are higher ranked and which schemes are lower ranked. What doesn't the algorithm consider? Here are some factors. First of all, availability of starting materials. Cost is another. And actually, I'll kind of show you the scoring tab here so you can see some of these as I talk about them. I mentioned cost and yield. Looking for convergent schemes. Those schemes that are highly branched are much more efficient than those that are long and linear. Efficiency of atom usage. We see schemes like this one we just discussed where Bach group is used. None of these atoms are incorporated in the final molecule. But protecting groups are a very necessary thing, and that's why we give you options to choose from. Another is complexity reduction. As we go from the product molecule back to the starting materials, the molecules get much simpler, less functionality, fewer rings, lower atomic weight. So the algorithm measures that step to step and scores those transformations that make more progress towards simplifying the chemical matter. One other factor is the amount of evidence to support a transformation. Very important to be able to assess that the chemistry is indeed validated. These are some of the characteristics that come under consideration. When I initially started presenting the retrosynthesis tool to customers after its initial release, many of them expressed the desire to have influence over the scoring algorithm the tool uses in order to produce the scheme that's best suited for their specific situation. And this has been a capability our product developers have been working towards for some time. With the latest product update, the scoring tab has been added to the retrosynthesis tool right here, and I was showing that to you. And let me show you in action. I'm actually going to pull up another tab where these have already been activated. And if I turn on the predicted and then the scoring, here we can see what different things the user can control. And it may have gone unnoticed, but when I initially launched the scheme, the experimental came back very quickly, but you saw a little spinning circle here next to predicted. It takes the predicted rules a little longer to run as it's looking for different ways of performing the transformation that's involved in adding B to C to give A. It won't have the exact same functionality, but it's closely enough related that may be a potential alternative to be used in a given transformation. So once the predicted steps come back and you activate them, as I said, you now will have the ability, I talked about a number of factors. These are the 5 that you'll have the ability to control. Complexity reduction, convergence, evidence, yield, and atom efficiency. And we did discuss those all a little bit. This is a fairly new capability. We're looking forward to people getting out there and using it from time to time. I've had access to it, and I can say a couple of things. First, the 2 factors that seem to have the largest impact on producing schemes of high yield and low price are the characteristics of yield and convergence. You weight these heavily I tend to see schemes come back that have lower prices, higher yields, things like that. But please feel free to explore other characteristics fully, as I will. We've already discussed atom efficiency. If your scheme will depend on the use of protecting groups, you may want to drop that in importance to get schemes of your liking. Just food for thought. So let's apply the characteristics as I have them here and see what we get. So right now, this scheme, before we initiate that, has a 51% yield and $351 to make 100 grams. And once we apply that, let's see what we get. Scheme looks a little different. Different disconnection in the first step. So let's go to the overview and see, wow. So estimated yield now has gone up to 84%, and our costs of starting materials have gone all the way down to $90, which is less than $1 a gram. So hopefully you will find this is a valuable tool in making the process of developing efficient schemes even easier for you.
Excuse the interruption, Gary. Since this appears to be an attractive route that has been generated, could you show how I might find supplier information for starting materials, please?
Absolutely. Pricing information for a given starting material or intermediate can be viewed by clicking on the supplier's hyperlink that's associated with those compounds that do have suppliers in our ChemCats database. I'll just select this one here. And we can look at the different vendors for cyclopropane carboxylic acid. Vendors are asked to supply a few different pieces of information: a CAS registry number, name, purity, some provide a hyperlink to their own website, pricing information, if available, and then we ask them to provide some availability information. First of all, do they keep it in stock? And second of all, how quickly can they ship it? You can see I've got 88 suppliers for this material. Something we've done to make it a little easier to determine which company to select is that we provide some filters over here on the left-hand side. If we are looking for a specific supplier, we can click that over here. I need to do some stuff quick, so I'm going to select those places that I can get it within a week, that maintain it in stock. I want to minimize the chances I get notified a few days after I order that they are out of stock. So, and then lastly, I'm based in the United States, so I would like to make my order from a company from which I don't have to worry about customs. Notice that there are a number of countries specified here. So depending on where you work or where the synthetic work will take place, a supplier in that country may be available. So I will select the United States, and then I have the ability here, I'm down to 15 suppliers, I have the ability to download this information either as a PDF or as an Excel spreadsheet, which makes it a lot easier, especially if you have a purchasing function within your company. They would usually really appreciate that.
The example you've been discussing involves a retrosynthesis for a known compound. Can this tool be used to find a pathway for a novel molecule?
Indeed it can. This is one of the greatest strengths of this tool, and Jana has a really nice example that will highlight this capability. She'll show that off in just a minute. I would like to go back to our original scheme and point out that in addition to experimental steps, which are published examples of an exact transformation, and we see 4 examples of that here, the retrosynthesis tool can also provide published examples of similar transformations called predicted steps. We've already discussed how these steps take a little longer to find than the experimental steps, as the tool looks for other reactions with slightly different functionality that accomplish the same transformation. So we have this scheme right here. It's a good scheme, but let's say we happen to be in this portion of the synthesis, and we experience a problem in obtaining one or both of these starting materials. It's out of stock, whatever. So we need another alternative. With predicted rules turned on, it will bring back both experimental steps and the predicted steps. So the experimental steps will always be shown first. And let's do that for this one here, and we'll see that the first 9 examples are experimental, and then as we get past that, we'll see it turns from purple to green, and those are the predicted steps. So we can explore one or more of these, and I will pick one for our purposes. Let's examine this one, Once again, our scheme was originally 51% yield and $351. And we see by making this substitution, the yield went down slightly, but the price dropped. So, not only have we been able to get around a bottleneck, but potentially we may just have innovated. We may have found a better way to make the compound of interest. So it has just a tremendous amount of potential to do both. And I hope you all discover that when you engage the tool to address your retrosynthesis needs. So that's the end of my portion. And I'd like to turn things over to my colleague, Jana, now.
Looking to the Edit Plan options, could you go into that section and describe each one of these options, please?
Sure, I'll pick another demo example for this. So what I'm going to do is to search for an actually known compound first, ametopterine. But I'm not interested in the synthesis of that existing compound, but in the synthesis of an not yet existing analog. So what I'm going to do is to click on that structure, which gives me the option to edit that structure. So clicking on Edit Structure will give me the structure editor with that compound prepared. And I'm now removing that methyl group and changing this nitrogen bridge to a sulfur bridge. And instead of this benzene ring, I'd like to have a pyridine moiety at this position. Searching that compound first as a substance will show that we don't get any as drawn results, also no substructure results, quite some similarity hits with sulfur bridges indeed, but combined with the benzene ring. We also see that pyridine moiety, but only in combination with the nitrogen bridge. So to start a retrosynthesis for a compound where we don't have such a structure hit, we can use the option to start it directly from here. So when we have our compound of interest in that small window, we can change the search type to reactions, and then this Create Retrosynthesis Plan button will pop up. Please note that you also will see a link just below that button to set the plan options before you submit the retrosynthesis for calculation. So that would be the place to change the plan options immediately. I'm not going to submit that retrosynthesis plan because it would take some time for the calculation, but I'm going to open the plan from my saved results. So I'm clicking on the star button. I set up a tag for the plan option results to find it a bit faster in my saved retrosynthesis plans. So here we actually have the different retrosynthesis plans with different plan options assigned. You can also see here in your saved results which options have been applied. So that would be the plan without changing any options that you would receive then. And I'm going to open that one. And we will get a very nice plan immediately with the first disconnection as a predicted one. Also that disconnection is a predicted, and as soon as we have the experimental steps available, then those will be merged with the predicted plan as well. Going to the Steps tab, we see that we already with the default options have quite a nice amount of alternative steps. So we can either click on this link or open the alternative steps by clicking on this Erlenmeyer flask and review the alternative steps from here. But 90 alternatives already take some time for further review. Nevertheless, for some compounds, you might receive less alternatives, or you just would like to see a broader diversity of the alternatives. And in these cases, you can go to the plan options and change not only the synthetic depths to 4 to get one additional disconnection that might bring you to even cheaper retrosynthesis when one more step is needed. And you can also change the rule set that has been applied. So by default, we use only those rules that have a lot of evidence reactions in the literature. We will provide more information on the different types of rules and how they are created in another session, so please feel free to sign up for this session as well. So here, to get a broader diversity of alternatives, I'm going to select the rare rules, which contain all the rules that we have in our rule set, also these rules that have less evidence reactions. And create a retrosynthesis plan will then provide or start the calculation for the new plan. I'm going to open the finished plan from my saved results. So here we have the plan with the rare rules. And as we had already 90 alternatives with the common rules, we now would find even more alternative steps. In this example, nearly 300. And those will, of course, also provide a broader diversity of reactivity, transformations, functional groups that are applied, so that you have a broader choice.
That is a great deal of alternatives. Could you show some efficient ways to navigate these choices?
You're absolutely right, Daryl. So actually, no one would like to browse through this huge amount of alternatives. And to narrow these alternatives down a bit, we actually have two more settings available in the plan options. So going to the plan options again. On the right-hand side, we see two features. The first one is the break bond tool, so we can define a bond to be broken in the first disconnection. This can be applied to one bond. The other feature is the protect bond option, with which you can protect multiple bonds to be broken throughout the whole retrosynthesis plan. So those bonds will now not being touched during the retrosynthesis. I was curious to see here some examples or some alternatives that keep the nitrogen on that heterocycle, because a lot of plants will end up with glutamic acid, like this one here. So here, scrolling a bit further in, we see also glutamic acid as the starting material, and I'm now actually interested in those plants having a different starting material. I would now click on Create Retrosynthesis Plan again, but will open this from my saved results. I calculated those plans with the common rule set as well as with the rare rule set, so that we have a comparison between the rare and the common rules. So I'm going to open both of them. And having a look at the steps overview, we now see that we have, instead of 90 alternatives, only 6 alternative steps left for the first disconnection. With the common rules and with the rare rules, we see that we have now 20 instead of nearly 300 steps. So we will save a lot of time scrolling through these alternatives by narrowing down those alternatives using these bond settings in the plan options.
From what is shown, common rules provides plenty of alternatives. Why would one consider uncommon or rare rules even?
For many substances, you get very useful plans already with the default settings. However, exemplified on these plans, you will see, for example, here for the first disconnection, a interesting alternative. Let me open this in the meanwhile for the common plan as well. So here we have, scrolling through the set of alternatives, for example, also the option to apply the aldehyde in the reaction, or this carboxylic ester. within the common rule set, you don't see these options. So you will get some alternatives providing a broader diversity, and that's the reason why calculating a plan with rare rules might still be beneficial, even if you have already quite a significant amount of alternative steps with the common rules. But as I said, quite often you get very nice plans with the common rules as well. So please feel free to submit with the default settings first. And just if you think, well, I actually would like to see a bit more, then go ahead and change the plan options to see if you get a bit closer to what you really can apply in your lab for your real-life molecule.
Does the retrosynthesis tool provide any information on experimental procedures for the individual steps?
Sure, it does. Let's go back to the alternative steps for this rare rule plan. So here in the third alternative, for example, we see a lot of evidence reactions, a bit more than with that halogen describing chlorine, bromine, or iodine. Here the leaving group is a bit broader. That's why we have more evidence reactions. We can go to the evidence reactions by clicking on this link. This will always open in another tab so that you don't lose your retrosynthesis plan. And these evidence reactions will of course not show the exact reaction that you would like to do because the molecules don't yet exist, but it will show you similar reactions to what you would like to do. So we have the thiol here, and the leaving group in this first reaction actually is not a halogen, but another leaving group that might be very suitable for a reaction conduction. So these reactions are ordered by kind of relevancy, so that you ideally would find immediately reaction conditions that you can apply for your target molecule. However, we quite often have some functional groups in our target molecule that are not in the evidence reactions, and for this we have, of course, all the filters that you know from normal reaction answer sets that you can apply to the set of evidence reactions as well. You see, for example, here reagents and catalysts. Catalysts all displayed with their full names. Also solvents can be filtered. You also will find some reaction notes when you are interested in some specific types of reactions. And we have the search within results feature here as well, when you would like to refine with a structural moiety. So let's try this. So actually what we see here is in the beginning, or the first reactions have a thiol group connected to a chain. What I would like to see preferably are these types of reactions where the thiol group is connected to a heterocycle, because that's what is represented in my target molecule, or in the starting and the intermediates for my target molecule as well. So I can draw this by using a variable, the heterocycle, and I'm going to draw the sulfur group here. I can also protect the sulfur group against further substitution, and I'm going to draw the sulfur group here as well, connected to a carbon atom. Can also assign this bond to be formed in the first disconnection and have this in the reactant and in the product. You could also use the search within result to draw functional groups, specific functional groups that shall be present in the reactant and also be present in the product without any changes. So kind of non-participating functional groups that shall be tolerated in case you would like to prevent the need of protecting group chemistry. Click on OK and refine this as a substructure to give us already a more specific set of reactions. I mentioned already the option to also refine by non-participating functional groups, and additionally to the possibility to do this in the structure editor, we have kind of a more general option for these groups, where you can select substance or functional group classes to be tolerated in your reaction. And what we have additionally in our retrosynthesis plan is a carboxylic acid. So I'm going to select carboxylic acid for the non-participating functional groups. And instead of 14K reactions, we now only have to review 43 reactions to see if those are suitable for our real-life synthesis. And to now get to the experimental procedures, we have 3 options in SciFinder N. The first one is the experimental procedure that has been there already for a long while. So here we have a copy and paste out of the original source. We see also here the precipitation of the final product. Of course, this always have to be adjusted for your real molecules then, but maybe this might work as well with the filtration as a cleanup. The second option to access the full synthetic procedures that we now have in SciFinder N as well is the methods now synthesis protocol, where you have a step-by-step procedure available that you just can print out, take to the hood, and then conduct the synthesis like this. And the third one is the option to go to PatentPak. So let's go a bit further down the list so that we see also some examples on that page a bit further down. So here we have also a nice example fitting to our refinements. And here we can access PatentPak via the interactive viewer, for example, taking a look for our either the substrate or the product. So here we have the carboxylic acid and a thiol. Click on that page link, and here we end up directly with the synthetic procedure, which is very often the case when you go to PatentPak from a reaction answer set.